Okay, let me know if you can't hear me on YouTube. But, well, today we'll be talking about a little bit about evaluation first. Then we'll do our surprise bonus activity. Okay, let me know if you can't hear me on YouTube. But, well, today we'll be talking about a little bit about evaluation first. So, and then we'll talk about sets. And if we have time, we'll talk about text. But I suspect that we won't be getting to text, so I might do this on Tuesday, but it's not going to be in the exam if I don't cover it today. Great. Any questions about projects before we get started? Or anything else? Great. So, yeah. It's from everything that we didn't cover in the first midterm. So that includes the Tuesday where we had the midterm. But yeah, nothing from before that. Other questions? There is definitely the Tamara Mansner paper, and I don't exactly remember which ones I had listed in my slides, so I'll go through that and post this on Slack after the lecture. Remind me if I forget. Okay. So evaluation. Evaluation is important to, if we build something, we want to think about how is it good? Did it work? We talked about evaluation a little bit when we talked about perception and we talked about crowdsourcing, right? So this isn't completely a new topic. I just want to take up a little bit more generally what is evaluation and how do we do it best? And so the goal of evaluation is to avoid ineffective visualization solutions, but also to justify solutions. And I guess higher level goal of evaluation or validation would be to generate knowledge that we are certain about, right? Because if you build something and claim that it is great, we can argue that it is great, but of course it's good to have facts about whether it's actually useful. And there is a lot of differences between if you want to evaluate perceptual effects, is it easier to read values of a bar chart versus a pie chart, and a complete system, right? So these are completely different things, and you're probably not going to be able to make a quantitative statement about comparing systems. But you might be able to make a statement about this interaction technique that I'm thinking about, or this complicated visualization that I'm designing is better than the competition, right? And then the other thing that you want to think about is, do you want to validate something that is unique, that you build as a probe, and where there's no alternative, or does your solution compete to something that's out there, right? So, for example, if you develop a new node link layout algorithm, very clearly there's alternative node link layout algorithms. So you probably would want to do some comparison. But if you solve a specific problem in a domain collaborator's lab, there's probably not another solution that you can compare to, right? So you have to really think about validation for this one technique. And then the other thing that is orthogonal to this, which is kind of I think more common in industry, not so common in academia, is usability testing, but it's super useful even in academia, right? So if you build a system, you just want to test usability. Can people, are people using it the way you think? Because it turns out when you develop software yourself, you know where to click, right? You know what to do. And you will be very, very surprised if you give a software piece that you developed for the first time to a user. It's always very, very painful, right? Just don't click over there, and so on. Okay, so here's an example. This is a study that we did. I showed this at the beginning when we talked about perception. Here we wanted to study these different highlighting techniques, right? We had these highlights in the text here that are kind of tricky to see sometimes. Then we had these static visual links here, and then we had these fancy routed visual links that didn't include anything. And so we kind of came up with hypotheses here, and the hypotheses were that the visual links lead to a better performance, are faster than conventional highlights. And the context-preserving visual links do not have a negative impact on correctness. And so those were these two hypotheses that we postulated. Then we ran a formal user study. We even used eye tracking. We had people answer the questions. And then we did look at the results. And what we found is that, yes, in fact, the average search time and the average misestimation is the worst for the traditional highlights. Note that this down here, right? This is a bad chart. I didn't know better in 2011 when I did this. What would I use instead of this bar chart with error bars? A violin plot, exactly. And the 95% confidence interval, right? Statistics and how we report statistics has changed a lot since 2011. So the other thing that we did, as I mentioned, is we did an eye tracker study on top of this. And the eye tracker study didn't actually give us anything quantitative, but it did give us some kind of qualitative assessment. So here are the eye tracker, the gaze for just the highlighting conditions where there's no links. And what you see is that this is actually fairly distributed across the screen, right? But if you look at the gaze for the link condition, you can see that these are actually very concentrated around the links, right? So people don't actually have to go off with their eyes and search for other items. They're very confident about, this is the things that I have to look at. It's very salient, and it basically looks the same for the context-preserving visual links. On the other end, on the other extreme, is this kind of like domain-specific tool that we built, right? Where we help people analyze data like these genealogies of suicide cases. And there isn't really an alternative, right? There is not another tool that you can just do comparison and say this is like 20% better or anything like that. And so what you typically do in this case is to use something that's called a case study. So you would describe how like a domain expert finds something with your tool, and ideally something that they couldn't find before or that they didn't know before. So you demonstrate the usefulness to a scientist. And that's another established techniques to validate your tools. Let me see. So generally, there is this spectrum here from for evaluation methods. There is this kind of like this extremely controlled experiment where I'm extremely certain of what causes the differences. These are kind of lab studies or crowdsourced studies where I really very carefully vary my conditions. And then on the other side, I have this like case studies where it's just like one system out there, right? They actually, I can't really tell why my system is better. I can just say my system does something good, right? But the benefit of these down here is that they have high ecological validity, right? So that they apply in the situation, like you've used it in this situation. If you use this tool to analyze suicide data, you know that it's useful to analyze suicide data. But if you have made some claim about, my node link layout is better for tracing path, it's not completely sure that this has a relevant impact in practice, right? The ecological validity isn't super high here. And in between here, you have interviews and questionnaires. This could be unstructured or structured or semi-structured, and you have field observations or lab observations, right? And so clearly, if you deploy a tool and observe how people use it, you get very high ecological validity. And interviews are somewhere in between. They can be super useful, but of course, you just ask people what they think, and you don't actually see them do something. So there's many different methods for evaluation. There's like algorithmic performance measurement, heuristic evaluation, which is basically just, you build something and then you let experts review it and give them some forms to review it using some recognized methods or usability metrics. There's usability testing. This is like often done with thinking aloud tests. So you give people a user interface, you ask them to do something, and you ask them to externalize what they're thinking, right? They think, oh, I can't find the button that I have to click next or something like that. Then you can record that, and that helps you understand what is going wrong. A very cool paradigm is the Wizard of Oz study. So sometimes we want to study stuff that we didn't implement, right? Because it might be super difficult. So we might study, can I use natural language to perfectly specify what I want to do in a visualization? And you could build a system where you actually speak to a human operator in another room, and that human operator is very skilled with the visualization tool, and they would just build the visualization that you asked for, right? But then if you do that, you can study how are people asking these kinds of questions, for example. And so there's a couple of really good Wizard of Oz studies out there. You can do eye tracker evaluation. I talked about this. You can do expert evaluations, or you can do insight-based evaluations, where you let people like analyze a data set and record their insights and then count and quantify the insight. And you can do log analysis. So if you've actually deployed a tool, you can look at the logs of how are people using it. And then we can collect a lot of metrics. And I'm not gonna, there's lots of objective metrics such as task completion time, errors, or % of tasks completed, and many of these others here. And then there's subjective metrics, things like, did you think this was good? Which one did you think is better? How satisfied are you with what you just experienced? You can ask people about their subjective performance. You can ask people about intuitiveness and so on. And so both of those are valuable, and often you combine both of them, right? I guess the big dichotomy here is quantitative versus qualitative evaluation. Quantitative methods are all about objective metrics and measurements. They use numbers and statistics for interpreting data, whereas qualitative methods are subjective metrics. They describe situations, events, people, interactions, observed behaviors. They use quotations from people about their experiences, attitudes, beliefs, and thoughts. And so, you know, there's very different tasks, very different questions that they can answer with these methods. Some people are hardcore, I'm a quant person. Other people are hardcore, I'm a qual person. My personal view is that you should really pick the methods based on what you want to learn, right? Like if you want to study how like a social group accepts technology, you're probably not going to go for quantitative measures, right? You're going to go for some qualitative process. But if you want to know like performance of a new visualization design where you have a clear competitor, then you're going to go for quantitative methods. So I mentioned this issue about validity a little bit, and this is like very important. So there's this concept of internal validity, and the question that you can ask here is, can you trust the experiment? Like, do you know what you learned is true, right? And this internal validity is high when tested under controlled lab condition. And so you can with high confidence state that the observed differences are actually because of the test conditions, right? Whereas external validity is about, is your experiment representative of real world usage? And this is high when an interface is tested in the field. For example, if you use a handheld device and test and run a test in a museum, for example, to explore the collection. And so what you learn from that is are the results valid in the real world, but you don't actually know exactly what led to these results, right? So the trade-off is really like more akin to real world. The more akin you have something to a real world situation, the more your experiment is susceptible to uncontrolled sources of variation, right? Because then, you know, lots of things can go wrong in complex real world scenarios. And then recall, this is from the design study methodology paper, right? The scope of evaluation is different of where in the design phase you are. You have pre-design, design, prototype deployment, and redesign in evaluation approaches, right? So if you're like here, the pre-design phase, you can kind of like observe and interview target users. If you're in a prototype phase, you can like see if a visualization has achieved its design goal to see how a prototype compares with the current state of the art systems. And if you have deployed, you can kind of like assess the visualization's effectiveness and uses in the field by looking at, does it actually influences your audience's use case? So the other thing that I kind of like to hark back to a little bit is Jaak van Wijk is like a pioneer in the visualization field, and he's a very reasonable and smart person, and he's like a very prototype, invention, new techniques focused person, and he's kind of like jokingly somewhat saying, develop new methods, interfaces of software that are so awesome, cool, impressive, compelling, fascinating, and exciting that your reviewers, colleagues, and users are totally convinced just by looking at your work in some examples. So maybe your tool is obviously so much greater than anything else that you don't need to run a quantitative or qualitative study on it. That's something to aspire to, but of course not always possible. Okay, any questions about evaluation? So if you're interested in this topic, there's like plenty of classes, right? There's like a human-centered computing concentration for masters and PhD students. There are classes such as HCI, advanced HCI. There's statistics and research design. There's product design and development. There's ethnographic methods. There's introduction to research design and so on. And all of these classes can kind of like dig deeper into this. And I acknowledge that this was like a very short and cursory treatment of evaluation. Okay, so next I want to talk about sets. So I mentioned this a few times already, but like I worked quite a bit on set visualization. We also have a current grant on set visualization. But what started me off this path is this particular paper here. This is like a letter in Nature, like an article in Nature And that article here described the banana genome, right? And the banana genome is interesting to know about because we want to understand, like, what kinds of diseases is a banana vulnerable to, and how related, evolutionary related, is a banana to other plants. And so they actually use this figure here to visualize the banana genome, and I call this the infamous banana Venn diagram. And I might have shown this in the, I think, very first lecture, right, as an example of a terrible visualization. And you all now have the skills to tell me why this is a terrible visualization, right? But in brief, there's a lot of things that are wrong with it. For example, I can't actually spot which is the biggest intersection and which plants participate in that biggest intersection, right? So there's no proportionality between the size of the data and the size how it's represented here. It's super hard to trace, right? And so this is really a figure that was kind of probably made to make the paper look nicer, right? And to be some like graphic sugar on top of it. And I saw this and I thought, this is terrible. We have to do something better than this. And it's actually not an easy problem. So here you see this, like, there's a very big intersection up here with 1,151 shared genes right next to one with 40 genes, and they have equal prominence on the screen, right? So clearly a problem. And then down here you have like a gigantic segment that has only 105 shared genes. And so what this isn't an isolated incident. We've seen this many times in publications. And so, I want to now let you think a little bit about this problem. And so we'll be using in our exercise now, we'll be using a data set of the Simpsons. The Simpsons are Lisa, Bart, Homer, and Mr. Burns, and there's a few others here. And then we have certain characteristics. So for example, Lisa is female and is in school. Bart is male and is in school. Homer works at a power plant and is male. He also likes Duff beer. Mr. Burns is evil. He works at a power plant, and so on, right? And so these are our sets because, like, obviously we see that there's two people that are in a school, and then we have attributes on top of it. And so what are some of the questions that we would like to ask, for example? So is it, well, we could ask, for example, are people that are in school predominantly female, right? Probably not, right? Or are people that work at a power plant predominantly male? Or are people that work at a power plant also in school? These are the kinds of questions that we want to ask. Or we can ask things like, are people who work in a power plant, what is their average age, right? And is that average age different from the people that are in school? So these are the kinds of questions that we can ask. And so I want to start now with this design workshop where I would like you to work in groups so you could get to know the data. Take about 5 minutes to do this, and then create 2 rapid prototypes. I think on here in the text I might say 3, but just let's stick to 2. And let's do this like 2 times 5 minutes. Then do like a brief documentation of your 2 favorites in 5 minutes, and then upload to a bonus Canvas Dropbox by the end of the day today. So the Dropbox will basically close as soon as we, like an hour after we leave this room, right? So everybody who's here gets to participate. And if your solution is in any way reasonable, you will get like your bonus point for this workshop. Okay, so the questions that you could ask here and that I want you to think about is, what is the biggest intersection? Which set makes up an intersection? How big is an intersection? Does it work for more than 4 sets? Do attribute values correlate with an intersection? And just a tip, I've seen that people tend to always draw the people, and that's a valid design, but maybe think also about sometimes you don't actually have to draw the people, right? So if you draw a Venn diagram, the people are, for example, not explicitly drawn. Okay, so it's 20 minutes after 2. We'll spend like 15 to 20 minutes on this. Sure. Can you hand some back? Right. Thank you. Okay, great. I've seen a few solutions already on the Slack. So let's take a look at some of them. You're welcome to explain yours, or I can give it a shot. Like what this person here want to briefly say what they did? Okay, so this is a bipartite network layout, right? You kind of took the classes and then you took the people and you draw both of them and then you draw the edges between them. Yeah, that's a great solution. And then here. This is very cool, like a very creative solution. I guess I would probably call this Euler diagram. You'll see later, but it's like a very special take on it. It's very nice. Then up here. Horizontal dimensions of the sets. So we have vertical and we have horizontal ones. Okay, cool. The top one, it looks like mostly a matrix, right? And then, yeah. Yeah. And so you have, again, a bipartite or not completely, right? You have kind of like smartly placed the nodes, looks like it. Yeah. Okay, two types of nodes, the bigger one for the people and the smaller one for the attributes. Cool. This one here on the right. You get to click on the different attributes, you get to see how many people are based on different categories, and then to encode the age, get an Instagram for the issue within that. Okay, cool. Yeah, this reminds me of a technique that we'll later see. Very nice. Then we have this one up here. Like that where the intersections are by all of the bars stacked on each other. Mm-hmm. Yeah, so like the probably like stack it together like it kind of doesn't. No, but I think this makes sense, right? You have like a row here for school, and then you draw wherever that person intersects, right? So this is actually like a published technique that we'll be looking at later. So very cool. Down here. Okay. Okay, cool. Then we have one here. Oh, yeah, this is a very like a very scalable approach, right? Here you could have 1 million items in your data set, and that would just work as well, right? So that is like one thing that you're losing is higher order intersections, right? So you can't actually read, is there like people that are in school and drink Duff and are evil? But for like the pairwise and for very large data sets, this is actually like one of the best solutions out there. Okay, well, let's see whether somebody else has posted something on Slack since. Oh yeah, I see a few. Wow. Let's look at this one. Any volunteers to explain this? Yeah.
Categories, that's on the outside of Earth, and then Mars, the insect the number of sex. So what is power plant and our nail?
Okay, very cool. This is also a published technique. It's called radial sets. And then this one looks very similar. Yeah. Okay, cool. Great. And then let's see. Here we have one more. Got it. Oh, cool. That's a very creative solution. It's like reminds me of a star plot. Awesome. Wow, there's many now. We have our Venn diagram, or actually a Euler diagram. Yeah, that definitely works. Cool. Then did I miss one here? Oh yeah, here.
So that component is just a simple node graph, but I'm stealing area proportion to age. We don't have many types. Each link is colored according to position, and each bubble is colored according to gender. Yeah.
Okay.
Related from the and second one, sunburst diagram. I'm just writing the age.
Okay.
Yeah, you can select people on the right of the whole.
So this is interactive only for one person at a time. Okay. Yeah. Okay, cool. And then we have another chord diagram here. Have you recognized theirs? Oh. Okay, well, great. So this is awesome. I'm really glad we have so many different solutions, and it's kind of like very nice to see that, you know, even in like an exercise in 20 minutes in the class, you can come up almost with all of the set visualization literature together. So let's look at this a little bit more structured. So, you know, the big thing about in sets is, of course, Venn diagrams and Euler diagrams. And so the difference, what it is between a Venn diagram and a Euler diagram, is that a Venn diagram always shows all possible logical combinations, even if they're empty, right? So they always show every single intersections. In Euler diagram, we saw one of those. They show the logical relationships, and they may omit empty intersections, right? So here's like a Euler diagram of the relationship of the kind of like different geographical entities in the British Isles, for example. And here would be like our Venn diagram that has this intersection. Even if there are, like, there is no overlap between animals and minerals, this is still shown here, right? So there would just be a different label in here. And Venn diagrams for many sets are hard, like we saw the banana Venn diagram, right? If you look up Wikipedia, higher order Venn diagrams, you see these kinds of things. This is like what they used for the banana Venn diagram. There's like these other weird shapes. But this here is probably fairly readable. This is a 4-set Venn diagram, right? And a 3-set Venn diagram is great because it kind of teaches us, we know this from math, right? This is like how intersection works. They're intuitive. We can scale them. A 4-set Venn diagram probably also works, but then once you get into these kind of like non-contiguous shapes, it gets really hard, right? This is like mathematically possible, but not actually particularly sensible. The other thing that you want to try is you want to, like, if you want to do data visualization, we want to make them area proportional. And this turns out to be actually very hard, harder than you would expect, mathematically speaking. And in a Venn diagram, generally, like, you can't actually draw an area proportional Venn diagram in any case, right? That just doesn't work. And especially if you want to constrain it, like, for example, if you want convex shapes, which is kind of important to see the relationships, it becomes an extremely tricky problem. And so you have these layout criteria that are like, it's supposed to be area proportional. You want to have simple curves, at least convex curves. Circles are best. And that makes it easy to identify which sets are in an intersection. And it also has the Gestalt principle of good continuation, right? So like here, for example, we don't actually know which triangle is which exactly, right? But so yeah, there's a few techniques out there that can do this for 3 or 4 sets, but they also are heuristics. There's no, that they don't really usually actually calculate a true solution. And then the complex versus simple shape here is, I think this is, everybody would very quickly agree that this here is the better diagram than this here, right? Because I can just very quickly identify which sets participate in an intersection. So Euler Ape is one of those tools that you can use to create those shapes. But even in Euler Ape, you create these shapes, and we kind of know already from like studying perception, right? We know that the size of these shapes are kind of like hard to tell apart. So which of those 2 shapes here is bigger? Who thinks it's the left one? Who thinks it's the right one? Okay, maybe a majority for the right one, for the left one, and many people undecided. And so in fact, it is the left one, right? But it's difficult to judge. And so the pros and cons are, Venn and Euler diagrams are very familiar. They're very intuitive. They work well for 2 to 4 sets. And so if you have a 2 to 4 set problem, you should probably go for Venn or Euler diagrams. The cons is it doesn't scale, and area proportional is hard to do. It's also not well suited to show attributes, right? So I couldn't actually show attributes on top of a Venn diagram. So if I wanted to show ages on top of a Venn diagram, I would be stuck. Here's like a Euler diagram that shows these kind of like complex nestings. And this is very similar to one of the designs that we saw, right? So maybe also similar. This one here is maybe slightly similar to the roadmaps. But this one here is like a more traditional one. So you can create those things. They're fairly readable. You have to think a little bit about the algorithms. They can be quite useful. You can also do these sets on top of a fixed layout, right? So here, this is this bubble set example. This is here the African countries on like some kind of public health data set. You can see that the African countries here are connected by a shape. And similarly here, there's pizza restaurants in New York City connected by a violet shape, for example. And you can also do this with lines or these branching lines, line sets or kelp diagrams. Then we've seen a fair number of your designs here had these node link techniques, right? So where you treat the sets as nodes and connect to elements that are in that set. And so here would be an example of something like this, right? So here are research papers, then down here are research topics, and up here are authors, right? And so you show these relationships in this node link diagram. So that's definitely a solution if you want to kind of like explicitly represent both your items and your sets. And so here's just like from a previous version of this class, people have drawn this, something like this a few times. And then we also saw this solution in today's in some of the submissions today. This is the pairwise overlap, right? The matrix where we have the heat map, where we kind of like count essentially the number of intersections between two items. And as I mentioned earlier, this is the most scalable solution, right? That can have like arbitrary large data sets. And so if you have, and a lot of sets as well. And so if you have a large data set with 50 sets, this is probably where you want to go. Yeah.
Is there any way to make like pairwise overlap anymore? Because like when you show that, like half of that data is just a read.
Yeah, that's true for all matrices, right? So you could potentially, if depends a little bit on your data, you know, there's different solutions. You could, something that people do is they show like a detail view down here instead of the second triangle. But I do think it's actually sometimes useful because that way it works in both reading directions, right? So it's probably worth the space. Another thing that people have done is set matrices. And so here, these are actually whale sharks in the Atlanta Aquarium. Each of these rectangles here is one whale shark. And then each of the cells, like this is a grid. There's like in total some like 150 or so chemical compounds that they found in these whale sharks' blood, but some of them are not in everyone's blood, right? And so it's basically a black cell if this compound wasn't found, and a blue cell if this compound was found, right? So you have kind of like a card for each shark, and then you can actually do operations by shuffling, like by stacking these cards, right? So you can see both like whale sharks that you're looking at have these same compounds in their blood, or they have what are the diverging ones, and so on. And so this is kind of great for many sets and few items. So if you have like 10 items or 5 items, but many sets, then this could be a really good technique. We have seen a solution like this in today's designs. This is kind of like a linear diagram. So here would be a Euler diagram, different nationalities and how they intersect. And then here would be the linear representation, right? And what you could do is you could kind of see if there is an overlap along this direction here, then there's an overlap between the sets. So there's an overlap between French, Hungarian, and Italian. There's an overlap between French, German, and Hungarian. There's an overlap between French, Hungarian, and Welsh, and so on, right? So you can, this is how you read this. And that also works well. It's an interesting solution for sure. I saw something like this before in some of the designs that we had in previous versions of this class. As we did today. And then we saw a few of those today, radial sets. And so the idea of radial sets is that sets are segments on a circle. It's basically a chord diagram, right? And the relationships are encoded as ribbons. And so here you have like fruit, green, vegetable, red, and you have these connections. And it's a little bit tricky for higher order connections, right? Because that gets harder to see. Or it's like by default, this isn't possible. But there are extensions for higher order connections. I'm not sure I'm showing them because they are very messy. So I didn't even include them in the slides here. So basically, you could kind of like have another thing in here that connects to higher order connections. And then here, this is also designed for attributes because there's histograms in the segments that show the degree here. And so here are some examples of what people designed in the past. Okay, so then I want to talk a little bit about the set visualization technique that we built, this upset tool that's about visualizing intersecting sets. And so we were thinking about, can we take this kind of encoding and replace it with like a perceptually efficient visual encoding? And can we also use this tool to create some complicated slices like queries? So for example, what if I wanted to get a summary of all of the 2 set intersections, right? But not the 1 set or the 3 set ones. And how can we visualize attributes efficiently? And so like the example I'm going to be using is movie genres here. And so we have in the columns here, we have action movies, comedy, crime, drama, thriller, romance, horror, sci-fi, war, mystery, and some others. And you can pick them. This is kind of, and then you see the size of this intersection here. And then next to it, we have properties or attributes that we can visualize. And then we show like a table of elements and let people specify queries. And then we show attribute details. So this is like very fast. Now I'll just break this down a little bit simpler. So the way this works is you have like here's my Venn diagram. And what we're doing is this matrix-based layout. We have 3 columns, A, B, and C, that corresponds to our 3 sets. So what we then do is we kind of like create a row for every possible intersections. And so we do this by kind of like creating this row here. Because these are white cells, it tells us these elements here must not be in A, must not be in B, and must not be in C. Here they must be in A, but not in B, not in C. So this corresponds to this blue part here, right? And then I keep building my matrix like this, the B's and the C's, the just B's and the just C's. And then I start doing combinations. This is now the AB that you see over here. And then you have the AC, and then finally the BC. And at the very end, you have the ABC intersection between all of them. And now I have this nice matrix, and I can plot the set cardinality, or the size of these intersections, very easily with bar charts, right? So that's kind of like the trick here. And so now you can very quickly see that in this case, in this data set here, this is the biggest intersection of them all. And now, because I have this nice layout, I can also plot attributes very easily. So for example, I could plot a measure of how surprising the size of a particular intersection is, given the size of the sets that is shown as bar charts here on top. Basically, you know, if I have 2 very big sets and 1 very small set, I would expect that the intersection between the 2 big sets is also big, right? And so we can kind of quantify this, and we can plot this as a deviation from what we expected if this were randomly distributed. Or we can plot the attribute distribution. So for example, if we had age distributions here, right? And then this would be like the A set would be the school in The Simpsons, then you would kind of expect that the distribution here is left skewed because children are in school, right? And so here is an example of this, how this works in real life. This is the system, like the simple solution to it. You can kind of like hover over the rows or the cells, and then you can also do interactions on top of it. So you can, well, actually, let's look at this first. Here, what we see is the biggest 2-set intersection is between comedy and drama. And that kind of like makes sense because those 2 are actually the biggest sets, right? But it's also weird that comedy and drama, who kind of seem to be slightly opposite in terms of their intention, that they are the biggest set. And so we kind of, if we look at the surprise value of this, it's actually less than we would expect it, just given the size, right? So this is still the biggest set because it has the most movies in it together, but it is less than you would expect. And then similarly, we can look at the ratings here. So if we compare drama, comedy, we can see actually they have fairly high ratings on average, right? If we compare this to action comedy, which are not particularly known for the high quality, right? We can see that they have much worse ratings. The cool thing is that this also allows you to sort. So you can ask a question like, which is the biggest intersection? You can sort by cardinality and you get the answer immediately, right? Or you can, yeah, here's an example of how you can do that. Or you can sort by some other metric like deviation, or you can sort by a particular set. So you want all the comedies or all the dramas up here with you. And we can sort by degree, which is kind of like what we initially started out with. Then we can plot elements and attributes here in more detail, right? So, for example, we could ask, how do documentaries compare to adventure movies? And so, like down here, I've kind of created these aggregates here now for documentaries, and we see, first thing we see is documentaries don't mix much. There's not a lot of action documentaries, right? It's a documentary. There's a lot of action adventures, or there are plenty of action adventure children movies, right? So there's lots more going on here in the adventure bracket. And if we plot the documentaries up here, this is release date versus the average rating. We can see that they actually have pretty high rating, and we don't have a lot of historical documentations, right? If we compare that to the adventures, what we can see here is that the spread in terms of the rating is much, much higher, right? So there's lots of bad adventure movies. People don't rate documentaries very badly. One thing that's interesting is it looks like adventure movies have gotten worse over time, right? If you look at this chart. Do you think that's true? Probably. It could be true, but the thing that to be wary about here is that this is 1980, right? And of course, this is an internet-based data set. And so people kind of tend to forget terrible movies from the 30s or 40s, right? We keep a record of good movies, but we don't necessarily keep a record of the bad movies. And so there might be some data collection bias here, right? So we can't actually draw that conclusion. So the cool thing about this tool is that we built this as an interactive visualization tool where you can upload your data on a website. And it was nice to get, it got us a great paper, but then in the end, not so many people used it. And then we built a simple version of it that was implemented in R, and suddenly people started using it, right? So this has like a few million downloads now. And probably because people need to plot these set diagrams. And if you are in your R workflow, it's easy to just add this plot, right? But it's more difficult to export the data set and go to the web. And so it's kind of like a lesson for like meeting people where they are with their visualization tools, as opposed to doing something complicated separately on the web. And so here's the banana chart. So what you can see about this banana chart is like the banana chart here. The first thing we can see is the by far biggest intersection, and you probably would never have guessed from this chart here, is the one that has all of the plants. So we have 6 different plant species here. So like basically this tells us these plants are obviously all evolutionary related, right? And then we see the banana here is, this here is the banana, so the third row from the top. So we see that these kind of like there's a cluster of these 3 plants down here that have the biggest, the second biggest, and the third biggest intersection. So it looks like these 3 plants here are more related to each other than, for example, to this one here is the date. So the date seems to be evolutionary fairly distant, right? You see, except for the first one, it really only intersects with the others down here. So like, this is like not a super easy chart to read, but you can actually read something meaningful from it, right? And you can do some data analysis with it. And so what's really cool about this is now people have started to re-implement this. I'm aware of 12 different implementations out there in Python and in R and in Tableau and multiple JavaScript versions and so on. And so you can actually, if you ever want to use that, you can do that. And somebody actually designed this in a previous version of a class in this exercise. There is also a state-of-the-art report on set visualization by the people that did the radial sets technique. So if you want to dive deep into set visualization, this would be a resource that you could look at. So with that, we have 5 minutes left. I don't think we need to start text visualizations in those 5 minutes, but I'd be happy to take questions about set visualization, the exam, or anything else. If not, then let's just call it a day for today, and then I'll see you all on Tuesday. Yeah. Yes. Yes.